The state of quantum computing. I want to do two things in this episode. First, I want to talk a little bit about the theory of quantum computing and where I see the interpretation today. And this is a little bit controversial topic. I think science is not clear about how to interpret quantum theory and quantum computing. Now I'm going to make an effort to try to elaborate my understanding of it. And then I want to talk a little bit about where we stand in terms of quantum computing in general. The reason I'm talking about this is because quantum computing has been a focus at Orange Capital Partners. It has dropped a little bit on the list of priorities just because of the investability and the prospects of making money in the next 3 to 5 years, I think have been pushed out a little bit. But this is certainly a field that we're incredibly excited about, and there will be a time when Orange Capital Partners will actually make money with this. It's just not right now. This is a Not Even Wrong podcast. It's July 20th, 2021. This is Krim Delco. Since the last update, the fund is up 1.4%. The market is flat. We're down 3.5% for the year. The market is up 13.7%, but underperforming by 17.1%. Now, let's talk about the interpretation of quantum computing or quantum theory, and then talk about quantum computing in general. I am heavily influenced by Brad Hall, David Deutsch, John Preskill, Sean Carroll. These are the people that I have been looking at in terms of understanding what's going on. I've also spent in the sort of 2015 to 2017 timeframe. We have actually very aggressively educated ourselves in the field, attended conferences, spoken with people. I went to a winter school in Switzerland by a Swiss company. The name eludes me right now. They are in the quantum sensing space. They invited me, and I had the chance to talk to some pretty heavyweights actually in quantum computing. Arthur Eckert, one of them. He's a PhD out of David Deutsch's sort of circles. So other people, one IBM researcher, again, a big heavy name eludes me right now. It doesn't matter. It's not important. I don't want to name drop here. I just want to give people a sense for how it works, because the purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. And this is what happens sometimes. You spend time, you travel, you talk to people. I went to a quantum computing conference in Chicago. I went to one in Zurich. I went to one in Gstaad in Switzerland. So 3 conferences within about 1 year. And that's important. Like you have to understand deeply what's going on. I'm not an engineer, so I always say, look, I'm not going to go as far as actually making one myself, but I want to be able to ask the relevant questions. And I think I got to that point around 2017, and then we kind of dropped the ball a little bit just because there just wasn't enough tangibility in terms of quantum computing. Doesn't mean it's a bad field, doesn't mean it's useless or any of that stuff. By the way, it's so interesting and so fascinating that even if we don't make money, I think it's worth the time. I met with Rigetti Computing, for example. Also, that's how I got into, let's say, how I met Vijay Pandey, not in person, but I came across his work, and I think he's one of the few partners in venture capital in Silicon Valley that I definitely feel inspired by. He just has this nice balance between science, curiosity, and business that I hope I strive to myself. So let's get back to the interpretation of quantum computing. So where do we stand? We have this sort of spooky action at a distance. We have this situation where we have the double slit experiment. We have things that are happening that we observe that we can't explain with classical physics. This is the fundamental problem. This is how quantum computing was born. And the problem in particular is that, for example, we have a light beam that goes through a slit, and then we have certain observables. We observe certain things that we just can't reconcile with the idea that light is either a particle or a wave. And the answer to the question of what's going on in reality in the multiverse interpretation, which is the one that I'm influenced by most, because again, I am influenced by David Deutsch and Brad Hall a lot when it comes to the interpretation, and also Sean Carroll, and they are proponents of this. And the reason I like this idea, or I like this this interpretation, is because it's the one that brings logic and making sense to the theory of quantum computing and quantum physics and to Schrodinger's equation. So what it says is that we have an electron, we have a photon that goes, I'm talking about the double slit experiment now. So you shoot a photon through a slit, and that photon is going to interact with other photons, and also what they call shadow photons. And what's going on is that we have at any moment in time, at any, let's say at any time that the clock ticks, whatever that clock is, but anytime the clock ticks, we have a split of the universe, or we have the same photon being split into two, and then four, and so on and so forth. And those other photons in the David Deutsch explanation are shadow photons. They exist in other universes that are not tangible to us, but they do exist, and they do interact with the ones that we are actually see, that we have tangibility with. So the point here is that we have many, many more, we call it universes. The one that's tangible to us, the one that we can measure and see, and the one where we have sort of actionability, is the one that we live in. That's our universe. The others are, let's call them parallel universes, or universes where these shadow photons also exist, and they do interact. They do interact with the tangible photon in our universe. So that's why we have these weird results in quantum, in reality, and that's what we call quantum computing. Now, the name quantum comes from the lowest possible, the smallest possible entity. In the case of light, it's a photon. In the case of electricity, it's an electron. In the case of other things, it's an atom, and so on and so forth. I don't want to go to that level of detail, because also it eludes me a little bit. What if you split an atom? What if you keep splitting, and so on and so forth? But the point here is that I think what's really relevant for my sake to understand quantum physics and quantum computing is that we have the Schrodinger equation, which explains all the possible positions that an electron can have. For example, now let's take an electron, okay? And it is actually real in the sense that all these positions are taken, but only one is in our tangible universe. The others are in the shadow universe, or in the parallel universes. And that's why we were confused in the beginning, and we talked about collapsing and things like that of the wave function. But those electrons exist, and they are in those parallel universes, and they do interact with the tangible electrons. They do interact. That's why we have these spooky results in things like the double slit experiment. So this is sort of the lay of the land as far as multiverse interpretation of quantum physics is concerned. Now, what does this mean for quantum computing? Well, because we have information in the parallel universes, we can use that information. We can use these shadow electrons, for example, or these shadow particles in terms of computation. We can use them to do computation for us. This is David Deutsch's fundamental thesis. He became famous by, I think, proving that you can actually do quantum computing, that is possible. So he combined quantum theory and the theory of computation, and he developed a proof that quantum computing can increase speed of calculation and solve certain problems that are not solvable in classical computing, etc. So the reason that's possible is because these shadow particles, these shadow elements that are existing in other universes that are not tangible to us, they are still available for calculation. This is the way I see it. This is why quantum computing is interesting. Now let's talk about how can we manifest this in particular. So what is the problem then? Why don't we just build quantum computers? Here's why. Because whenever we have we have an interaction with a quantum a particle, that particle loses its coherence, so it decoheres, and it falls into all these shadow universes, and we lose the ability to use those shadow particles for computation. So what we want to build is a computer that sort of keeps its quantum state, or keeps the quantum state of the particular substrate that we're using for computation as long as possible. This is sort of the name of the game, and things like ion traps and superconducting materials, and then other things like superconducting is one, and ion traps. Those are the two I could think of. I think there's also captured cavities in crystals as a potential. So there's different approaches to capture certain substrates, physical substrates in the classical world, in our tangible universe, that exhibit this ability to communicate with the multiverse. Let's formulate it like that. I don't know if that's physically, technically, mathematically correct, but this is how I understand it. So these substrates, let's say an ion trap, is nothing but a physical substrate that allows us to bridge our universe with the other universes and use the information from those other universes in a controlled way, to do mathematics, to do a calculation. And the reason, there might be a contradiction in the sense that we're saying, well, when we do the double slit experience, don't we communicate with the multiverse because those other shadow particles do interact with the non-shadow photons? Yes, but it's not controlled. So we want to do it in a controlled way. And the way we do this is by having certain physical substrates, such as ion traps or superconducting materials, that have this, that exhibit this quantum, have this Schrodinger equation type distribution of all possible positions, in the sense that we are accessing other universes. And because we are able to do that, we have this luxury to do math at a scale and speed that classical computing wouldn't allow us to do. So this is, in a nutshell, the way I interpret quantum computing now. So we're bridging from quantum theory to quantum physics to quantum computing. This is the bridge that David Deutsch has built for us. Others, of course, also. Sean Carroll as a popular podcaster, John Preskill as a physics professor at Caltech, and so on and so forth. So lots of people have done that, but I would say Deutsch is the most, the one that comes up most, because also he's doing TED Talks and all that stuff. So this is where we stand now. In terms of technology, what does this actually mean? So let's say we have a quantum computer that works with superconducting materials. I visited one in Zurich, two actually, one in the IBM research lab in Zurich, and the other in the Polytech in Zurich. The professor there was kind enough to show me. They work with superconducting materials. And what's interesting about this, so we have this now, we have this physical substrate that exhibits the ability to access other than just our universe. So we have this access to the multiverse through materials that are in a coherent state. And then we can do certain calculations. We can use certain types of calculations, certain types of mathematical functions that in classical computing wouldn't make sense. For example, we can use the fact of interference, for example, interference. So we can say, well, how about we use the fact that maybe some positions within the Schrodinger equation space, some of those positions accentuates themselves and other positions eliminate themselves. So we could use, for example, that ability or that characteristic of the Schrodinger equation for our mathematical purposes. We could use also, we have, of course, the concept of entanglement, which is another, let's say, how should I interpret entanglement? Now, entanglement is definitely, I'm now in very uncharted waters. I don't think people have been able to explain entanglement even in the scientific world very intelligently. But the way I see entanglement is, again, it is the communication between universes that is somehow able to proliferate into our universe. Again, that's information that is being sort of used. It's not just in our tangible, but also in the multiverse, information that is available to us. And I think entanglement is one of the big sort of frontiers. Also, John Preskill talks about it a lot, using entanglement as an explanation for for things like gravity and the curvature of space. Again, way out of my league here, but I just think that because it exists, because the actual thing, the entanglement exists, we have to take it seriously, and it's very useful also, of course, for quantum cryptography. Now, what does it really mean, entanglement? Let's say in quantum cryptography, the way entanglement is being used is that we have a certain, let's say, we have two particles which are entangled. If we send them from Alice to Bob and somebody interferes, then we can see when Bob reads the information that it has been interfered because of the physics of it. What does that actually mean? It just means that if somebody interacts with an entangled quantum substrate, then there is information from the multiverse being written into or read into this particular substrate, and therefore Bob can read information, let's say it was interfered with. So this is something that the classical world doesn't allow. This is something I think Arthur Eckert has built his reputation on, in a sense that he's been the father of one of the quantum cryptography approaches using entanglement as a well, let's call it an elegant way to do quantum cryptography. So to summarize, excuse me, actually, no, I don't want to summarize yet. So I just want to get back to the substrates, ion traps, and superconducting materials. To my knowledge, those two are the most prolific actual technology hardware substrates that are being used in quantum computing at this point. Companies like IBM, Google, Microsoft are very active in the space. We also have lots of research labs. The way we see it at Orange Capital Partners is that we're just not ready yet to invest because it is not in our realm of investing into things like where technology risk is at a point where we still don't even know if it's going to work. The thing is also, I have a feeling, now this is me really just thinking out loud here, that we're probably going to invest at a point when the substrate doesn't matter anymore. So when we're at a point where the hardware is as far developed to the point where we just don't care anymore about substrate, if it is ion traps or if it is superconducting, it's not going to matter. What we're going to care about is that computers are able to work in a way that they can take advantage of this bridge between tangible and multiverse, and tangible universe and multiverse, and do calculations that are not possible in the classical world, and therefore from that perspective simply enable new problems to be solved. And this is key. We're not talking about problems necessarily that are existent now, that exist now. We're talking about the ability to solve new problems that we can't even solve with classical computers. And this has happened in the world of technology many times before. For example, when we had the internet, then the first sort of idea was, okay, well, we can solve problems from the pre-internet world, well, buying books, things like that. We can do that more elegant. But then we have, of course, things like, I don't know, YouTube and social media and things like that, which completely sort of change the way people do business, people do work. Actually, I can't even go further back when Thomas Edison developed the first thing, which was sort of like a camera. The first thing they did is record a theater. That's why we still call it a theater when we go to the cinema. In fact, of course, this was the first sort of tangible fruit. The first problem to solve is how do we record a performance in theater. But of course, from there, the movie industry came, and there's many more different types of applications of the camera today, and much more interesting than just recording the theater. So in that realm, I think we will see the same thing happening in quantum computing, that maybe the first couple of approaches will be, okay, how can we do things that we're doing now better, more efficient, but then we're very quickly, I think, come to the point where we can solve problems that are that we don't even know that we have them today. The point here is, I think what quantum computing probably can do the best is, and this is Richard Feynman, is simulate quantum situations. So, for example, take I always use the photovoltaic as an example. Right now, the photovoltaic industry is kind of stuck in just finding the best possible crystals to extract energy from the sun. But what if we could create an artificial material that is many times more efficient than the crystals that we have today? What if we could find the most optimal combination of existing materials that will absorb the light and create electricity? For that, we could use quantum simulation, and those are I think the most interesting applications that I can see right now, and that's where we as a fund are very excited about. So to summarize, the multiverse interpretation hinges on the fact that we have information in other universes that we can use to do computation in our tangible universe. We need to find the best possible substrates that bridge our tangible universe with those multiverses. That's where the work is being done right now, and ion traps and superconducting materials are sort of at the forefront of this. And then we have also applications, and in our view at Orange Capital Partners, we believe that simulating materials to find more efficient photovoltaics, for example, would be one of the most interesting applications that we could think of right now. Thank you.